Yeah. Hi guys. Hi to for today. I think basically we are just sorry. Yeah. So I think for today, looking at another Leetcode question, and it's about flipping equivalent binary trees. So last time I think I solved the binary tree question, and as again I'm still picking questions. Let me know what questions you guys want me to do. So today I think it's flipping equivalent binary trees, another medium question. Let me know if you guys want me to do a hard question or an easy question. But normally I go for medium because normally if you're gonna do an interview, most likely we'll be tested on a medium question. So so for this example, they're saying that for a binary tree T, we can define a flip operation as follows. Choose any node and swap its left and right child subtrees. So let's say if I pick node 1 here in this question, its its left and right subtrees are 2 subtree and 3 root subtree. So I flip them, and obviously you can see that this one has been flipped and then this one has been put to the side. But beside that also, let's keep reading the question. A binary tree x is flip equivalent to a binary tree y if and only if we can make x equal to y after some number of flip operations. So basically they're saying that we can make one tree equal to another tree if we flip it a certain number of times. So if we flip some nodes or some subtrees a certain number of times. So I think in this example here, they say it's true. So obviously the first main one we can see is that one's left and right subtree, as they said, choose any node and swap its left and right child subtrees. One left and right children, 2 and 3 have been flipped. So the whole trees have been flipped. But then if they're flipped, we can see that 3 will come to the side. But then 3's left hand child would be 6. But we can see in this example, 3's right hand child is 6. So which means that for this 3 and all its children as well, they were flipped as well. So I think that's why they flipped once values, 3 values, and they said 5. So let's look at 5. So 5, 7, 8. So we see if we push it to the right side, it should still be 5, 7, 8. So for it to be 8, 7, they need to flip it again. So let's see the other examples. When they're empty, obviously it's going to be true. You don't have to really do anything. If it's this, it's going to be false because no matter how you flip this, it's still never going to give you the same thing. This one also. So basically, if one of them is empty and one of them is not, it's never going to work. If both of them are empty, it's going to work. If in this case too, I think it won't work. It will work. Makes sense because this tree looks like 0 and then 0's left child is 1, and then the root 2 is like 0 and 0's right child is 1. So obviously if 0 and left child 1, if I flip it, I'll just get the first one. So basically just something like that. And once again, just going through the question. But I can pause the video, you guys can pause the video and let me know what you guys are thinking about how some approaches what you guys have thought about how to solve the problem already. From the looks of things, first thing that came into my head were, I think, as always I keep saying 2 things come to my head most of the time, but the first thing, one good thing with binary trees is normally you don't have to think about, as compared to strings and array questions, you normally don't have to think about optimizing because most likely you have to probably traverse the whole tree, and it's okay. Most interviewers are okay with that. So normally for binary tree questions, don't think about how will I do it in quick time or that. Just get a working solution. Most often than not, that's more than enough. But as I mentioned in a couple of videos, I mentioned for binary trees, if you're gonna do an interview and you have no idea of what to do, there, like, imagine you've not learned it. For those that have not learned it or those that are still confused, I mean, it still confuses me from time to time. There are some few techniques that I always recommend for anybody going to do a binary tree interview. You need to learn those things. Once you learn how to do them, those tricks can solve almost every question. And I think for this example, this is going to be an example of one of the tricks that I learned when I first did not understand binary trees at all. One technique that I learned that now I see its usefulness. See, I don't need to understand the question, but most likely, if you know how to do that technique, it will work for most tree questions, or you can tweak it just a little bit to solve the tree question. So one of the techniques that I recommend to all my friends and people is learning how to do a root to leaf path, like being able to find the root to leaf path of binary tree. So for this binary tree, if you can do like 124, 1257, 1258, you see that's a whole root to leaf. 136. See, once you can do root to leaves and you get all the each root to leaf path in like a whole array, normally you can do a lot of things with that information. When you get that, you can solve a lot of questions with that. You just imagine, even if imagine you don't know how to solve the sum of a tree, average of tree, all those things, trust me, once you can do root to leaf, you can solve a lot of questions. But also if you know how to do level order traversals, it can solve a lot of questions with that, or use that as a basis to solve a lot of questions. Same also goes for obviously the basic traversals like in order, pre-order, post order. Those ones too, you have to know them. So normally if you know these ones, plus if you know how to find the height, obviously there are some of them that you just need to know, like learn them. Find the height of a tree, find if you can find those things. You can do these couple of things, normally you'll be good with trees, trust me. But not all questions, but most questions you can solve them. And if you think I'm lying, try any binary tree question and try with these approaches that I mentioned: root to leaf, level order, all the pre-order, in order, post order, and finding the height of a tree. If you can do these things, most questions you see on Leetcode, you can solve it somewhere or another with them. And if you guys want, I can show you how I can solve multiple questions with that. So for this, let's not veer off. Let's go back to the topic. So we look at this question. The first thing that comes to my mind is obviously like a kind of level order. So it's like at every level I check. So let's say at level one. So at level one, obviously at every level aside level one. So if let's say I'm at level one, I check the next level's children. So if I'm at level two, I'll be checking the next level's children. So if I'm level one, I will check the next level's children. So 2 and 3. I mean that's level 2, which is has nodes 2 and 3. So first I make sure that this guy's left node equals this guy's left node value and this guy's right node equals this right. If they're equal, everything is okay. I don't do nothing. But if they're not the same, then what I do is then for this guy and this guy's values, I swap them. Like I swap the nodes. Like you just do root dot left comma root dot right equals root dot right comma root dot left. You do exactly that. And then once you do that, you exit and then you kind of go to the next level again with the update, and then you go again with the next level, each of them, each. So if I get to this level now, I check their kids, the left and right, and I make sure that the left and the right kid is equal to this guy's also level, left and right. Do you get it? If they're not equal at that point, but you notice that at this time, if I get to this level, this guy, this 2 node would be on the side. So 3 will now be here. So I check 3's 6, and then I make sure it's equal to this guy here. If it's not, I swap. Or if it's not, so I keep doing that till I get to the end. So that should work, but that will prompt the conditions and stuff. Another way that I thought that I said I wanted to prove is using root to leaf. So I'm gonna specify it. I was just looking through it and I realized. Now, you guys might not agree with me first, but take a look closely. For them to be equivalent or be flip equivalent, they have to have sort of like the same root to leaf structure. Because if the root to leaf structure is not the same, they won't be flip equivalent. If they don't have the same exact root to leaf structure, they should have. So what I'm thinking is they should have the same exact root to leaf structure. Just that it doesn't matter where the order of that root to leaf is. That's all I'm gonna say. So for instance, this guy has 136, but it's on its right side. This guy has 136, but it's on its left side. Do you get it? This guy has 1257, but this guy has 1257. Do you see? But in the end, you can see they still have the, like, for the root to leaf, for all the multiple root to leaves, they have the same root to leaves, but just that they're probably ordered differently in the tree. So basically, this question is simply, how I thought about it is, we just have to do the root to leaf of tree 1, do the root to leaf of tree 2, and then we sort both root to leaves and root to leaves we get in both tree 1 and tree 2. and we have to make sure they're the same. If the sorted root to leaf, so for this one, for instance, we will probably for root one for tree one, just gonna comment it out so you can see. So for tree one, we should get root to leaf. So this would be like the whole thing that contains all the multiple root to leaf. So the first root to leaf, you can get it, we get 1, 2, 4. Then the second one, we get 1, 2, 5, 7. Oh, sorry, hold on. Oh, yeah, sorry, 1, 2, 5, 7. And then the next one, we get 1, 2, 5, 8. And then the last one, we get 1, 3, 6 for tree 1. And then tree 2, we get, what do we get? The first one we get 1, 3, 6. Then the next one, what do we get? We get 1, 2, 4. Then the next one we get 1, 2, 5, 8. And then the last one we get 1, 2, 5, 7. Sorry, I should put this in bracket. So yeah. So do you notice what I'm talking about? Just look at them. You can see they have the same set of values, but just that they've probably been reordered differently. So all we have to do is just find a root to leaf. Because if you like think of it, if you don't have the same root to leaf structure, you're most likely going to be wrong. Like, I don't know how to explain it to make sense, but if you don't have the same root to leaf, sort of, it can be reordered differently. But if you like try it on a whole couple of examples, I've been looking at it for the first one. You can look at the second one like this. The root to leaf of them are going to be the same after this guy. The root to leaf after this, if I sort them out, they're not going to be the same. This guy, if I root to leaf, obviously it's not going to be the same. This guy, the root to leaf of this guy, you have a 0, 1 as a path. This guy too, you have a 0, 1 as a path. So that's why it's going to be the same. And that's why they say true. So you can, maybe I'm not perfect right now, but like as I said, I always solve it with you guys. So it's like I just walk through my ideas. And one thing about an interview though as well, the reason sometimes I just walk through it with you, it's like one thing about an interview is sometimes your interview question or your answer or your approach might not be 100% right. If your approach, if you were asked to run it through Leetcode, it probably would have gone through some errors. But the most important thing in an interview is your idea or whatever you pitch to the interviewer has to make sense. Your goal is to convince the interviewer that whatever you're telling him is right. It could not, like, it maybe could be 90% right. Maybe it works on only 500 out of like 520 test cases or something. But all they really care about is the general idea. Like, it's like as if whatever idea you pitch into them makes sense to some extent or makes enough sense. And if you can write out in code what you have pitched to them, that's it. That's it in an interview. If it's an OA, it's different. But if it's an interview like phone screen or on-site or something, your idea or whatever you pitch has to make sense. And what I'm telling you makes sense. For this to work, your root to leaf structure has to be like similar. If your root to leaf is not similar, you won't work. The only way, because if we flip, because we're not adding new nodes, we're not subtracting nodes, we're not we're not adding new nodes, we're not removing nodes, we're not like, all we're doing is flipping trees and subtrees. Do you get it? So even if we flip, your root to leaf has to be the same. And it's not like we're flipping both trees for them to look like something else. So it's not like if we're flipping this and then we're gonna flip this. Like, let's say if we push this here and we push this one. No, we're only flipping one of them to look like the other one, which means that this guy's structure, the only way this guy can, how do I say it? It's like, how do I give an example? It's like, let's say this guy is similar to this guy. We're trying to make guy A be exactly like guy B. The only way guy A can exactly be like guy B is that if already with guy A, he has a lot of features or his structure already resembles guy B, but he has a few differences. You get it? So when they have to have the same structure, so when we sort both of them, their structure, they should be the same. Do you get it? So that's why root to leaf works. They need to have the same structure. If this guy had like 1, 2, 4, 8, and then the other ones, no matter how many times we flip it, it will never be like this guy. Do you get it? So they have to have the same root to leaf structure. And you see, once I say that to an interviewer, it makes sense to him. Now he will be okay with it. All he asks me to do is just code it up. And once what I code makes sense, it might work on a lot of cases and stuff. But if it doesn't, If it doesn't work on all cases, he won't have the time to test it out. But once it makes sense and everything and it works and you can quote up what you've said, more than not, you have passed. Honestly, the worst thing he can tell you is maybe think of another way or something, but he can't tell you he's wrong, you're wrong, or as long as what you're saying makes sense. So you know what, rather than just talking so much, let's just go ahead and code up what we have. So basically, as I said, we'll find the root to leaf of both. So as you can see in the root to leaf, we have paths, multiple paths, root to leaf path, and we put them in a bigger path. So what we can do with root to leaf is, first, let's define some arrays, that because we need to be storing these nodes in arrays and stuff so that we can have the total thing. So we can have like something like, so path 1 for roots 1 or tree 1, and then path 2 for subpaths in tree 2, and then we can have the overall big one. So paths 1 for the big one, and paths 2 that stores everything. And we just know they're just going to be arrays. So just arrays. So basically just that. And then what we just have to do is, as I said, we just have to do, so we call a certain function self dot root to leaf, root to leaves, or root to leaf, yeah, just root to leaf of root 1, root 1, path 1, paths 1, and then we call self dot root to leaf, and then root 2, path 2, and path 2. I know, as I said, I saw with you guys, I don't even know, but like, that's what I think, and it might be wrong. I'm not afraid to tell you it's wrong, but what I know is, if you pitch this to an interviewer, there's no way he will straight away tell you it's wrong. The best thing is he will tell you code, because obviously he's not going to challenge you unless he has something inherent that says it's wrong, and unless he can dig up an example right on the spot. He needs to be able to dig up an example for you. But as long as it works for all the example he gives and the ones you give, he will just tell you to code it up. And if it works, he can't test it on all 600 or 1,000 cases like Leetcode does. Like, it's hard. So yeah, so you're good to go. So let's run it out and see. So we do stuff, and then what I'm just gonna say is, in the end, so both of them are gonna be in this one. So we just have to make sure we just can return sorted paths 1 should be equal to sorted paths 2. Do you get it? So basically this is it. So now we do the root to leaf. So that's why I said it's very good to learn root to leaf. But root to leaf, let's see. So if you've never learned root to leaf or know how to do root to leaf, probably today we can get a chance to go through it. So basically root to leaf is simply, as we're going through the array, we start appending stuff into the path, the smaller ones, path. See, we start appending stuff to it, and we, once we get to a child node, we append whatever that is in path, like this, path 1, like, oh no, whatever is in path 1 or path 2 to paths 1 or path 2, we append it to the bigger one. Do you get it? And then let's say I get 1, 2, 4. Now when I have 1, 2, 4 and I append 1, 2, 4 to the bigger array, I know I'm going to be going to 1, 2, 5. So what I need to do is that I need to remove the last element from the array before I go here. So basically that's going to be it. And then add, when I get here, add 7. When I know I'm going to come back, I remove 7 so I can add 8. So it's 1, 2, 5, 8. If not, I'm going to have like something like 1, 2, 4, 1, 2, 4, 5. And then 1, 2, 5, 7. 1, 2, 5, 7, 8. So you always want to make sure that when you get to the child node, after you append paths to the bigger one, you remove the last element from the array. That's it. So you're going to see it as I code. So I try not to talk too much, but probably people think I talk too much, but I'm trying to make sure everybody understands. So let's just go on. So define roots to leaf self whatever roots we have, and then whatever path we have, and then whatever bigger paths we have, the bigger picture. So basically we have our base case for almost every tree kind of thing traversal you do. This is like a given. Almost every tree thing you do, your interview will probably be expecting you to write this base case. If root is none, you return. This is like a big thing, even if it matters or not. It's probably almost going to be in every kind of tree structure you do. So if root is none, return. So what we said, at every root we're currently at, we append it to path. So path.append root.var. So basically now the next case that I said we check is we check if it's at a child node. So we'll still be checking, and then 'cause even if at a child node, it still needs to append the 7 before it makes that check. So we can check it now and see if root.left is none and root.right is none. That means it's a child. Honestly, if it's a child, what do we have to do? As I said, we just have to append it to path. So path.append path. So basically paths.append path, and then what we go next is we can either return, but we can go on and then get to the none and then just return. But after we do that, all we just have to do is just do the self the root.left. So imagine we're here, it's not none, we append one's value, we see it's not a left or right child, we see it's not like a child, a leaf node. What do? We just do a root.left and root.right, like traversal. So we just do self.root to leaf, root.left path to make sure it gets a copy, like Python, just however you do in your programming language, and then paths to store it, because that's the reason why, because you're getting stuff traversed, so you need to make sure you have a copy of path as you're going down every array. Did you get it? So as you're going down the levels, you need to have a copy of it path. Yes, so that's just the reason why I just do it that way. And Python stores stuff by, there is thing between by value and by reference, and I know Python stores stuff by reference, so let me know what you guys think. So this one we just want to store it by value, so that it doesn't keep changing stuff some way, but I'm sure you guys understand. This is basic Python. So self the roots to leaf, root.right. Basically almost every tree counter, so you're gonna have something similar to this, and then paths. So it stores in paths, and as I said, once you get to the end of the node, because imagine we're here at 7, if it finds, imagine we're here at 7, it finds that it's a child, so it appends the path to the bigger path. So now what does it do? So after it appends it, what it does is it's going to try and do root.left. So it does this guy's left, it's going to be none, it's going to return. Come and do root.right, it sees it's none, it's going to return. Now after it returns, we know it's going to return back to 5, but before it returns to 5, we need to, as I said, make sure that we remove path. We just only have the last value, like we remove the last one. So basically I could have done path.remove path.pop or something, but this is also good. Like I can just do this to that and -1. This will keep all the elements aside the -1. This is just slicing, and it works as well. So basically this should be it, and let's run it and see. Basically, as I said, like this is not even like a big deal. Let's just run and see what goes on. So as we can see, everything was true. Couple of them. Yeah, we can clearly see what's going on here. So there's just the first example. You can test out different examples just to see, and let's just run and see. But I'm glad with this solution, because if you see the solution to a person, even if we're wrong, I'm sure they're gonna be okay with it, as long as you can code it up and what you've coded up makes sense and supports your idea. That's it. Because you also don't want to pitch an idea and now he believes you and tells you to code it, and then now you can't code it. That's bad too, Yeah. So yeah, your job is just to convince the interviewer, but we're not sure. See, so perfect. I wasn't even sure. I swear I was not even sure. And if you want to see, this is my first time, because I don't know, I don't want to mess up the way the video thing works out. But as you can see, this is my first time ever doing it one time, and it works. And this is not like it's anyone's account. This is my own account, the one I keep showing to you every day. So this is it, and let me know what you guys think. Probably not the fastest, it's okay, but as long as your idea works. And trust me, interviewers are also interested in very new and genuine ideas. Not a lot of people are going to think about it this way to check. I've not seen yet, but I don't know what solutions are available, but I know this is my way I did it. Let me see if it's there in roots relief, recursion. See the first one, canonical traversal, right child, left child is smaller than right, canonical representation, and See, everybody has a different way, but see, I did it very different. At least it lets the interviewer know. Interviewers are also open to very unique and diversified ideas. So as long as you have a very diversified idea and it's different and you can support your proof, see, I explained to you why root to leave should work, and you see the importance of root to leave because you can have a root to leave question on its own, that you can be asked to do root to leave on its own. But have you seen that just with knowing root to leave, we're able to solve another question? With root to leave, you can solve so many questions. Trust me. If you like, go pick a binary tree question and try some root to leaves on some easy mediums. You see, you can use it to solve some questions. Sometimes it will not solve it all the test cases, but it will work for a lot of cases. Trust me. You can use root to leave on lowest common ancestor. You can use root to leave on so many. You can try it. Trust me. Like, see, that's why I advise people. It's actually better if you learn binary trees or trees so that you really understand it. So that if you see a problem, you're not like limited. It's better. But if you're constrained on time, you don't have time, but you need to learn trees, especially for like first year students or some second year students. You don't have time or something, undergrad, and you're just coming up and you want to learn it. And let's say you have an interview in like a week, you don't have time, you have to learn other structures as well. With trees, just learn root to leave, level order, in order, pre-order, post-order, find the height of the tree. And then there is this YouTube video that like helps you solve some binary tree questions easy. Shows you like how most binary tree questions structure is. How I say if root is non-return, you're almost gonna have it in every root traversal, tree traversal structure. And then do this left or right like this. You're always gonna have a structure like this. So if you can learn this main structure and then learn the ones that I've told you, trust me, you can solve a lot of binary tree questions. Like, it will work. So go ahead, hit likes, hit subscribe, and let me know what other questions you want me to solve, and I will do my best. But thank you once again, and hey, have a good one.